Hi, my name is Damir Pulatov. I'm a computer science graduate student at the University of Wyoming. And the title of this presentation is Opening the Black Box Automated Software Analysis for Algorithm Selection. And this work is done in collaboration with Maria Anastacio and her advisor Holger, and also my advisor Lars Kotthoff. First of all, what is algorithm selection and why should you pay attention to it? As it is known, many algorithms have complementary performance in different domains, such as SAT, CSP, and many others. And what that means is that one algorithm might work very well for one given problem instance, but it will have a much worse performance on some other instance. So then the issue becomes, which algorithm do I choose to get the best performance on all of the instances? And to motivate it even further, here's the chart that I made from SAT competition from the year of 2018. On the x-axis, there's a solver that won the competition, and then the y-axis is the solver that performed the worst. So the dots are the instances, SAT instances that were run on both of the solvers, and the diagonal line is the line of equal performance. What that means is if an instance is close to the diagonal line, that means that both solvers performed equally on that particular problem instance. And as you can see, most of the dots are in the upper triangle. What that means is that these problems were solved by a maple derivative solver within a few seconds, but they timed out on YALSAT. 5,000 is the cutoff time. But interestingly enough, there are a few instances that timed out on the best solver and were solved by YALSAT within a few seconds. What that means is that if there was an automated algorithm selection system, it would automatically capture this relationship and run maple derivative on all of these instances and run YALSAT on all of these instances. So how is algorithm selection done? There are many approaches to that, but in this work we're focusing mostly on the approach described as in the ASLib paper. We call this approach a black box approach. We collect problem instances and algorithms into a portfolio. We extract domain-specific features from instances. So if we're looking at the SAT solvers, we would extract things like the number of clauses, number of variables, and many other things. Then we run all of those algorithms on instances, we observe their performance, and using that observed performance plus the features we've extracted from instances, we build a model, one model for each algorithm, and use that model to predict the performance of those algorithms on new instances. Using that, we perform algorithm selection. And as I mentioned, there are many algorithm selection systems, but the common feature among them is that the algorithms are treated as kind of black boxes. We don't know much about them except their observed performance. What we're proposing here is what we call a white box approach to algorithm selection. We do almost the same thing, but on top of extracting features from instances, we're also extract features from algorithms. We build one unified model for all of the algorithms and instances in the portfolio, and then use that model to do performance prediction. Using those predictions, we do algorithm selection. So what are the features that we've extracted? There are two main feature classes that we looked at. The first one being features based off of the source code. So things like cyclomatic complexity, the size of the source file, and so on. And the features based on abstract syntax trees, or ASTs. So we collect the number of nodes, number of edges, the kinds of operations that a solver does, and many other things. For the sake of completeness, we also included what we call dummy features, which are essentially one-hot encodings for algorithm IDs. And the goal of those features is that we wanted to assess whether or not improvements that we see in our evaluation come just from the fact that we're using one unified model versus one unified model plus the new each features that we've extracted. We perform experiments on 10 different scenarios. For 9 out of 10 scenarios, the performance metric is the runtime. And notably for OpenML Weka 2017, the performance metric is the accuracy, since this is a machine learning scenario. And what are the results? So there are two metrics that we summarize that are of interest to algorithm selection community. The first one being MCP, which stands for misclassification penalty. It is defined as the additional cost that you incur if an algorithm selector chose a suboptimal solver. And the part 10, which is average runtime over all instances, and where the timeouts are multiplied by 10. We normalize the performance to the fraction of the gap closed between single and the virtual best solvers. So single best solver is like running one solver in all of the instances, which is what you would normally do if you didn't know about algorithm selection. And the virtual best solver is an oracle that always chooses the best possible algorithm. So numbers close to 0 mean that their performance is very similar to a single best solver. Numbers close to 100 mean that they're very close to the virtual best solver, and the negative numbers mean that the results are worse than the single best solver. We perform different experiments. So our baselines are the columns I and double I. I stands for the instance features, so the standard black box approach. The double I is the instance plus the ID features, so the dummy ID features. And the IC stands for instance plus code. IA, instance plus AST, and ICA, instance code plus AST, so all of the features combined. What we see here is that when we look at the MCP metric, we're improving in 8 out of 10 scenarios, and when we look at part 10, we're improving in 6 out of 10 scenarios, with one scenario resulting in a tie. To summarize, we see up to 26% improvement in MCP and up to 71% improvement in part 10. While this is not everything that we've done so far, we can only include so many results within the presentation. I encourage you to read our paper and to ask questions during the conference. So the current work includes extracting the binary features. So one of the challenges we faced is that many solvers do not make their source code available, which makes it very difficult to analyze based off of our current way of extracting features from solvers. So extending this approach to extracting binary features might prove very useful in those cases. And the work that I'm very excited about is extending the current idea of characterizing software and extracting features from software into algorithm configuration, which is a very similar problem, but instead of selecting the best algorithm for an instance, we're configuring an algorithm to get the best possible performance out of it. Thank you for your time, and I hope to see you at the conference.